You know, it really seems strange the idea you could teach something really complex, like advanced reasoning, with, well, almost no information.
Uh-huh.
But there's this new study out, and it seems to show just that, how just one single, well-chosen example can seriously boost an AI's math skills.
Yeah, the paper we're diving into is called Reinforcement Learning for Reasoning in Large Language Models with One Training Example. And they looked at this technique, RLVR reinforcement learning, with verifiable reward.
Okay, RLVR.
Right.
Yeah.
So basically, the model gets rewarded if it gets the math problem right. They use this to train large language models, LLMs, specifically for math reasoning tasks.
And the big question was,
Their core question was, what's the absolute minimum amount of training data you actually need? Could one example be enough?
which sounds crazy, but what did they find? The results were pretty staggering, weren't they?
They really were. The headline finding is that RLVR with just one specific training example dramatically improved performance.
Like how much?
We'll take the Quinn 2.5 Math 1.5b model. On a standard benchmark, Math 500, its accuracy jumped from about 36% all the way up to nearly 74%.
Wow, from 36 to 74% with one example.
Just one. And what's really interesting is how efficient that is.
Yeah, I mean, normally you hear about needing these massive data sets, thousands, millions of examples.
Right. And this single example achieved results similar to training on a subset of 1,200 examples from another data set.
One versus 1,200.
Pretty much. And they even found that using two carefully picked examples did slightly better than that 1.2K set and came close to performance from a full 7,500 example data set.
Okay, so this isn't just a one-off quirk with a specific model.
No, they saw similar boosts across different models,
Mm.
Quinn 2.5 Math 7b, Llama 3.23b, DeepSeek, and also using different reinforcement learning methods like GRPO and PPO.
So it seems robust. But what made these single examples, these magic examples, work so well? The paper highlights two, right? Pi 1 and Pi 13.
That's right. 1 and 13 were particularly effective. Let's talk about 1 first.
Okay.
It's described as an algebra problem, but it has a physics angle, so something about wind pressure, sail area velocity,
Right. A bit applied.
and the answer provided in the training data was 12.8. Though, interestingly, the actual calculated answer is slightly different, closer to 12.7.
Huh. And how did the base model do on this one before any training?
That's where it gets really interesting. The base model, Quinn 2.5 Math 1.5b, was already almost solving 1.
Almost.
Yeah, it got all the steps right except for the very last calculation, the cube root. And apparently, even without training, 12.7 was a common output.
So it wasn't learning the whole process from scratch. It just needed a nudge on that final step.
It kind of looks that way.
Yeah.
It suggests the model already had the latent ability, and the single example helped crystallize it, perhaps.
Okay, and what about the other one, 13?
Pi 13 was a geometry problem. It involved a circle going through 3 points and a line intersecting it. The answer was 43.
And the base model's performance there?
It also had some partial success, about 22% accuracy before any of this single-shot training.
So again, not starting from zero, these weren't impossible problems for the model initially.
No, not impossible, which again points towards this idea of maybe unlocking or refining existing capabilities rather than teaching entirely new skills.
And this leads into something else they found, which sounds really counterintuitive, this post-saturation generalization.
Ah, yes. This was one of the most surprising findings.
So the model learns the single example really fast, right? Gets 100% accuracy on it.
Very quickly, yes. The training accuracy on that one example hits 100%.
And normally you'd think, okay, now it's just going to overfit. It'll be great at that one problem and maybe worse elsewhere.
That's the standard expectation. But here, the test accuracy, its performance on new, unseen math problems, kept going up significantly, even after it had completely mastered that single training example.
Kept improving. How much?
With 1, for instance, after saturation, the average performance across 6 different test benchmarks improved by another 3.4%.
Okay, a noticeable bump.
But with 13, it was even more dramatic, a jump of almost 10% after saturation.
Wow. And that's different from what you usually see when training on many examples.
Quite different. With larger data sets, often the test performance starts to degrade slightly, even before the model has fully converged on the training data. Here, it keeps rising post-convergence on the single example.
But then things got even weirder, didn't they? Later on, the model did start overfitting the training example.
It did, yes, in a very specific, strange way. At much later training stages, when generating the solution for that one training example it learned, it started producing these really long, kind of nonsensical outputs.
Nonsensical.
like mixing in bits of other languages, just long streams of text, but still embedding the correct solution steps somewhere within the mess.
So it's acing the training example, but in this bizarre, verbose, multilingual way.
Kind of, yeah. And this is the crucial part, despite this weird overfitting on the training example,
Its performance on the test problems.
remains strong. Its reasoning on new problems was still sound, still human interpretable, and the accuracy stayed high.
That's fascinating. So the overfitting was confined to the specific training instance, but the generalized reasoning improvement persisted.
Seems so. And this overfitting pattern only emerged quite late in the training process after many, many updates based on that single example.
Okay, so this whole one-shot RLVR thing wasn't just about 1 in 13. Did it work more broadly?
Yes. The researchers found it was effective for almost all the individual math examples in their larger data set. We use one at a time for training.
And what about generalization between types of math problems?
That was another key finding. Cross-domain generalization.
Yeah.
Training on a single example from, say, geometry
Yeah.
often improved the model's performance on algebra or number theory or other areas.
So learning from one specific geometry problem could make it better at algebra.
That's what they observed, which is interesting because, well, intuitively, you might think training on geometry helps geometry most.
Right. But they found that wasn't necessarily the case. Training on an example from the same domain as the test problem didn't always give the biggest boost.
Correct. Sometimes training on an example from a different domain led to better improvement on a target domain. It suggests the learning is maybe more abstract than just memorizing a problem type.
Did they find combining, say, 2 or 3 of these good single examples always worked better than just one?
Not necessarily. The paper notes that simply adding more good single examples didn't always improve results over the best single example alone. Sometimes it did, sometimes it didn't.
Maybe a case of diminishing returns or interference.
Possibly. The dynamics seem complex.
Something else they noticed was an increase in self-reflection in the model's answers.
Yes, that was quite intriguing. As this one-shot training progressed, the model's generated solutions for the test problems started showing more phrases like rethink, recheck, recalculate.
Like it was learning to pause and verify its own reasoning.
It certainly gives that impression. It suggests the development of more, well, complex or cautious reasoning strategies, even from this minimal training signal.
So what's driving these improvements? Is it just the reward for getting the right answer?
Primarily, yes. The paper indicates the improvements are mainly driven by the policy gradient loss, essentially, the mechanism that rewards generating correct steps or the final answer.
Okay. And they distinguish this from something called grokking.
Right. Grokking in other contexts often involves a sudden jump in generalization after a long period of overfitting, and it's often linked to things like regularization, like weight decay. Here, the driver seems to be more directly the reward signal from RLVR.
Makes sense. And exploration played a role too, encouraging the model to try different solution paths.
A very important role. They emphasize the need for diverse exploration in the model's outputs
How did they encourage that?
by adding what's called entropy loss. Think of it as a penalty for the model being too certain or always generating the same kind of response. With the right settings, adding this entropy loss pushed performance even higher.
So rewarding correctness and encouraging variety helps.
Exactly. And get this, they found something even more surprising.
Follow.
Just using entropy loss alone without any reward for getting the right answer.
Just telling it to be more varied.
Basically, yeah. That alone led to a significant performance boost. For the Quinn 2.5 Math 1.5b model, it boosted Math 500 accuracy by 27%.
Just from encouraging exploration without rewarding correctness.
Yeah, and similar boosts on other models, too. It suggests merely encouraging the model to explore different ways of thinking can unlock some latent reasoning ability.
That's wild. One last thing they looked at was label robustness, right? What if the answer given for that single training example wasn't perfectly correct, like that one example where the label was 12.8, but the answer was closer to 12.7?
Right, they tested that. Small inaccuracies, like the one case, didn't seem to hurt performance much. The model still learned effectively.
Okay. What about bigger errors?
Well, if the label was substantially wrong, but in a way the model could easily learn to replicate and easily overfit wrong label, it could actually make performance worse than providing a completely nonsensical label.
Worse than a totally random wrong answer.
Yeah, because the nonsensical label effectively acted like having no reward signal, similar to just using entropy loss, which we saw could still improve performance. But the easily overfit wrong label actively taught the model something incorrect, harming generalization.
So a slightly fuzzy target is okay, but a precise but wrong target is potentially worse than no target at all.
That seemed to be the takeaway from those experiments.
Okay, so wrapping this up, this dive into the one training example paper shows some really mind-bending results.
Definitely. The sheer effectiveness of a single example with RLVR is the main point.
And this strange but beneficial post-saturation generalization where performance keeps improving after mastering the example.
Right. Plus the cross-domain benefits, the hints of increased self-reflection in the model's outputs.
And the importance of not just rewarding correct answers via policy gradients, but also actively encouraging exploration, maybe even just with entropy loss alone.
It all paints a picture where these base LLMs might have significant reasoning capabilities just waiting under the surface.
Latent abilities that don't necessarily need massive data sets to be coaxed out.
It seems a very small amount of the right kind of signal, like from one well-chosen verifiable example, can act as a key to unlock them.
It really makes you wonder then, if one example can do this much, how does that change how we should think about curating data or even understanding what's really going on inside these models?
Hmm. What other capabilities might be lying dormant, just waiting for the right little nudge to activate? It certainly opens up questions about data efficiency and the fundamental nature of generalization in AI.